Hi guys, welcome to my channel. Today I am going to explain about laws of planetary motion. These laws are derived by Johannes Kepler and they govern the movement of planets around the sun. So here we have two bodies, sun and the planet. The more massive body, sun, is called as the primary body and the other one, that is the planet, is called as the secondary body. These two bodies in space interact with each other through a gravitational force called G. So similar to this, that is to the movement of planet around the sun, we can consider the movement of satellite around the earth, where earth is the more massive body, so it acts as a primary body and satellite acts as the secondary body. And the satellite moves around the earth and they both interact with the gravitational force G. So, the laws of planetary motion governs the movement of satellite around the earth. So, it is very important to understand the Kepler's laws of planetary motion to understand the movement of satellite around the earth in space. So, now we will start with Kepler's first law. So, according to Kepler's first law, the orbit, that is the path taken by the satellite to move around the earth, is elliptical in shape. So that, which means the orbit is elliptical in shape. The shape of the orbit is elliptical. So as you know, ellipse has two foci, F1 and F2, and the semi-major axis A and semi-minor axis B, and we define the eccentricity E. So here eccentricity E and the semi-major axis A are very important parameters of orbit. So now we will move on to the second law of Kepler. So according to Kepler's second law, for equal intervals of time, the satellites sweep out equal area. That is, for a time duration of 1 second, the satellite is traveling a distance S1 and it covers area A1. And in the same duration, it travels distance S2 and covers area A2. Now, the areas A1 and A2 will be equal because the velocity S1, the velocity at S1 is greater than the velocity at S2. Because at S1, the satellite is very close to Earth and it is under the influence of gravitational force. The influence is greater here. So the velocity must be greater to overcome the gravitational force. But at S2, the satellite is far away from the Earth, so the velocity is less compared to the velocity at S1. So according to Kepler's second law, for equal intervals of time, the satellite sweeps out equal area. That is, A1 is equal to A2. And now Kepler's third law. According to Kepler's third law, the square of periodic time of orbit is proportional to the cube of mean distance between the two bodies, which is the semi-major axis. So we get T square is directly proportional to E cube and we use the proportionality constant 4 pi square by mu, where mu is the Kepler's constant 3.986 into 10 power 14 meter cube by second square. Now we can replace 2 pi by T by N, which is the mean motion of the satellite, and we get E cube is equal to mu by V square. So this is Kepler's third law. So we have completed 3 laws of Kepler, and now we are going to see about a very important question, that is, why the satellites are not falling on our head, which means how the satellites stay in space. So to understand this, we will see this diagram. Here consider Earth with mass capital M and satellite with mass small m. The satellite moves around the Earth in a circular orbit with velocity, orbital velocity capital V. Now, this satellite is under the influence of two forces, centripetal and centrifugal force. The centripetal force is the force due to the gravitational force. So, which is the gravitational force is pulling the satellite towards the Earth, but it is balanced by the centrifugal force, which is created by the velocity, orbital velocity of the satellite. So which means the velocity should be in such a way that it should create a centrifugal force which balances the centripetal force so that it makes the satellite to stay in space without moving towards the earth and falling on our head. And so by equating centripetal and centrifugal force, we can get the velocity of satellite in orbit, which is given by V is equal to root of gm by r, where g is the gravitational constant, m is mass of earth, r is the distance between satellite and earth. So now we can relate this to Kepler's second law, where we saw when the satellite is very close to the earth, that is when the distance is smaller between the distance between satellite and earth is smaller, the velocity is high, because the satellite has to overcome the gravitational force. So that is reflected in this formula. And when the distance increases, the velocity decreases. So now we can relate Kepler's second law with the velocity formula over here. So hope you got an idea about Kepler's three laws and the orbital velocity of satellite. Thank you.